Welcome to AI Paper Drop. I'm Alex.
And I'm Maya.
What if you could design a complex computer chip from scratch in 5 weeks, without writing a single line of code, and without a single human ever checking if the math was actually correct?
That sounds like a recipe for a very expensive paperweight. I mean, if no human is checking the work, how is it not just a hallucinated mess?
That is exactly the problem we have been stuck with for 60 years. In the world of high-stakes engineering, you have two choices. You can do it the fast way, which is basically write some code, test it, find a bunch of bugs, patch them, and just hope you didn't miss the one critical flaw that makes the whole thing explode.
The test and patch cycle. It is like trying to build a bridge by throwing rocks at it until it stops falling over.
Exactly. Now, there's a second way. It is called formal verification. This is where you use pure mathematics to prove that a system is perfect. No bugs, no edge cases, just a mathematical certainty that it works.
Wait, if that exists, why are we still dealing with software updates every Tuesday and chips that have critical vulnerabilities?
Because formal verification is a nightmare. It is painstakingly slow and incredibly expensive. It takes a small army of PhDs years of work to prove even a tiny piece of system. It was so costly that only the most exceptional projects like NASA probes or nuclear controllers could afford it. It created this hard ceiling on how fast we could innovate.
So, it is a trade-off. You either go fast and risk failure, or you go slow and guarantee success. But this paper claims they broke that trade-off?
They did. They call it the SALT method. And the core idea is that they stopped trying to make the AI be the expert, and instead made the AI be the worker, while mathematical kernel became the boss.
Okay, walk me through that. Usually, when we use AI to code, we are the boss, and we just hope the AI didn't make a typo. How is this different?
Imagine a high-speed assembly line. On one side, you have a fleet of AI agents. These agents are fast, but they are messy. They guess. They hallucinate. They try 1,000 different solutions per second.
Which sound like a chaotic way to build a processor.
It would be, if not for the kernel. The kernel is like an incorruptible referee standing at the end of the line. It is a rigid, mathematical gatekeeper. It doesn't care how the AI found the answer. It only cares if the answer is mathematically proven to be true.
So if the AI guesses a solution that is 99% right, but has one tiny error?
The kernel rejects it instantly. No questions asked. It just gets tossed in the bin. Because the AI can generate these attempts so quickly, it doesn't matter if it fails 999 times. As long as it hits the truth once, the kernel catches it and locks it in.
So the hallucinations, which are usually the biggest problem with AI, actually become ignorable noise. They are just the cost of doing business at AI speed.
Precisely. The human is no longer reviewing the code or the proofs. The human is just the conductor, directing the agents on what to build, while the kernel handles the truth.
This sounds great in theory, but building a RISC-V processor is an immense task. That is not just a simple script. Did this actually produce something that works?
This is the part that is actually wild. One single researcher, working on consumer AI subscriptions during their evenings and weekends, did this. In 5 weeks, they went from the high-level application code through a verified compiler, all the way down to the silicon boundary.
Wait, 5 weeks? For a processor?
5 weeks. They produced 320,000 lines of verified mathematical code. And they actually taped it out, meaning they sent the design to be physically manufactured on a silicon shuttle.
I am struggling to wrap my head around the scale here. 320,000 lines of proof is an astronomical amount of work for a human. To do that in a month without a single human reviewing the proofs it feels like cheating.
It feels that way because it breaks our mental model of expertise. But the paper includes a full accounting. They tracked every single error. They had an error ledger that went up to catch number 256. That means the system failed hundreds of times, but not a single incorrect proof ever made it into the final record.
So the kernel really did its job. It filtered out all the noise and only kept the gold.
And they didn't just stop at the chip. They used this same system to tackle the twin prime conjecture. They essentially used mathematical certainty to prove exactly why current human methods are unable to solve it.
Hold on. They used a chip design method to prove something about one of the most famous unsolved problems in number theory?
Exactly. Because once you have a system that can generate and verify formal proofs at scale, the application doesn't matter. Whether it is a processor or a prime number, the logic is the same.
So, if we can now build perfectly verified hardware and software at the speed of an AI prompt, what does that actually change for the rest of us?
It changes the unit of production. We are moving toward the era of the one-person company. Imagine a single architect who can lead an entire workforce of AI agents to build PhD-level hardware. You no longer need 1,000 engineers to ensure a chip is bug-free because the process itself guarantees correctness.
It is like moving from a world of guessing to a world of correct by construction.
Exactly. We are shifting from trusting the expert to trusting the process.
It makes you wonder what else we have been building using the test and patch method that should have been verified from day one.
Probably everything. The bottom line is this. The speed of AI discovery no longer has to come at the cost of the truth.
If you're enjoying this, follow or subscribe to AI Paper Drop wherever you listen. It really helps, and we have a new episode every day.
Paper by Jason Hickey, produced by AI Paper Drop.